Finding the internal energy is too complex a problem to solve. However, the internal energy of a system is independent of how we arrived at that system. Think about 50 grams of water at 25 degrees Celsius. Whether we start with 50 grams of ice at 0 degrees Celsius and warm it to 25 degrees Celsius, or start with 50 grams of liquid water at 100 degrees Celsius and cool it to 25 degrees Celsius, the 50 grams of liquid water at 25 degrees Celsius must have the same internal energy. The internal energy is what is called a state function. A state function depends only on the current state of the system. The current state of the system is determined by the temperature, the physical states, mixing, and some other things. So once those are known, that determines the state of the system and therefore the value of any state function. Since E is a state function, delta E is also a state function. Specifically, the value of E does not depend on how we get from the initial state to the final state, just on what those states are. This makes the calculation of state functions much simpler than the calculation of things that are not state functions. However, while delta E is a state function, Q and W are not state functions. In the example of a battery being discharged, if the battery runs a fan, work is being done by the battery, as well as heat being released. However, if the battery runs a heating element, then all the energy is lost as heat, and no work is done. In the two cases, delta E is the same if the initial and final states are the same. However, Q and W are not the same in the two cases. The most common form of work in the laboratory is when a gas is released from a chemical reaction, expanding against the pressure of the air. This type of work is called PV work, for pressure and volume. If the pressure is constant, then the work is P delta V. The units of pressure are force per area, and when that is multiplied by volume, we get force times distance. If the volume is increasing, then work is being done by the system, and the sign of the work is negative. So, since delta V is positive, and the pressure is always positive, and the work is negative, then W must equal minus P delta V. Enthalpy. Enthalpy is the second important energy function. It is the total energy of the system. We are most interested in the enthalpy when a change takes place at constant pressure, which is what happens for most of the processes that occur in the laboratory. Enthalpy is the sum of the internal energy, E, and the work done to create the space for the system, that is, PV. The mathematical equation is H equals E plus PV. Enthalpy is a state function. Therefore, the change in enthalpy, delta H, is also a state function. Delta H equals delta of the quantity E plus PV, which equals delta E plus delta the quantity PV. If the process occurs at constant pressure, then this becomes delta H equals delta E plus P delta V. At constant pressure, then, when all the work being done is PV work, we have the following. Delta H equals delta E plus P delta V. Substituting Q plus W for delta E, and minus W for P delta V, we get delta H equals Q plus W minus W, which equals Q. So at constant pressure, the change in enthalpy is the heat gained or lost. So, for an endothermic process, one where Q is positive, delta H is also positive. And for an exothermic process, where Q is negative, delta H is also negative. For any process, since the enthalpy is a state function, delta H is the enthalpy of the final state minus the enthalpy of the initial state. Delta H equals H final minus H initial. If we have a chemical reaction, it is usually written delta H equals H products minus H reactants, and is called either enthalpy of reaction or heat of reaction. Let's finish this lesson with some important facts about enthalpy. Number 1, enthalpy is an extensive property. That is, if we do twice as much of the reaction, we get twice as much energy released or absorbed. Number 2, delta H for a reaction in the forward direction is equal in size but opposite in sign to delta H for the reverse reaction. If we reverse the reaction, the sign of delta H is reversed because what were the products are now the reactants, and what were the reactants are now the products. Number 3, delta H for a reaction depends on the state of the products and the states of the reactants. If we have a substance in a different state, then we will have a different value for delta H.